Hi, in this video, I'm going to go over how to do the energy transfer worksheet or worksheet 7.3. Um, and the re one of the difficult things about this one is that there's lots of different options. So as you watch this, just think, like for example, you might have more or less blocks in a section, and that's usually fine. You might have energy in the E internals side of things, or you might have energy come out. So there's lots of different ways to set some of these up, but hopefully as you kind of like listen to me talk about it, you can kind of decipher whether yours is correct or not. So it doesn't necessarily need to be exactly the same as mine. Um, so there's more than one option here. So all right, so let's take a look at this first one here. We have it starts out with this cart pressed up against the spring. So I'm going to go ahead and put the cart and the spring in the system so that I can have, kinetic um, and elastic energy. I note that I'm going to also end up with gravitational energy because it's up high. That means I need to put the earth in the system. So I think those are the main things. You could or could not put the track in the system. If we were, if you were losing it, I'm going to choose not to. If you put the track in the system and you had friction, then that energy lost to friction would turn out in the internal category. I'm going to say that it is frictionless. In fact, most of these are going to be frictionless, unless I think only the train one is one of the last ones there. So, um, So obviously we're going to start out with all elastic energy because the spring is compressed. All that elastic energy is in the spring. So at the end, the cart is moving, so we're going to have some kinetic energy. It also is up high, so we're going to need to have some gravitational energy. And so let's see here. We could just do 2 and 2. That would probably work out just fine. So again, you could have any combination of kinetic and gravitational energy. Though the one thing I'd say is if you put, if you had 3 kinetics and 1 gravity, the problem that you would have is when you go to do number 2, it'd be a little bit tricky, because in theory, it should have less gravitational energy and more kinetic energy. So, right, this one's basically the same problem, except that it's just not up as high. That means it's probably also going to be going um, faster. So I'm gonna put, sorry, let me catch up here. Cart, spring, and earth. Um, so it's gonna probably only have 1 gravitational energy and 3 kinetics, right? So less gravitational energy because it's not up as high, but more kinetic energy as compared with number 1. So again, yours doesn't have to be exactly that way, but those are the things you should be thinking about when trying to answer the question. Again, I'm gonna go ahead and go with frictionless on this one. So as we pay attention to what we have a car that's moving. So this says the initial velocity is greater than 0 and y is equal to 0. So what this says is our gravitational energy is equal to 0 and our kinetic energy is not equal to 0. So um, let's put the car in the system, and we're going to have gravitational energy because it's going to go up the hill. So that means we should have the Earth in the system as well. Um, So that means we're going to start out with a bunch of kinetic energy. I'm going to start out with 4, gives me options of what to do with later, as opposed to if I just had, like 2, started with 2, that wouldn't have worked quite as great. Here it says the initial or the final velocity is 0, so that means no kinetic energy. It means that our gravitational energy is greater than 0, so basically all of that kinetic energy is turned into gravitational energy as it rolls up the hill. Next one, a person pushes a stalled car to get it to the service station. Okay, so this one's a pretty good example of where we want to pick our system fairly carefully. So I'm gonna still say that this is frictionless, though there is a fairly good argument for maybe saying that's not the case because how does the person push it if it's frictionless? Um, And basically, the reason I'm saying it's frictionless is because I don't want to have to like deal with energy lost to friction. So, um, but there's, it might be good to have it. I don't know. So maybe I'm oversimplifying it a bit, but okay. So you have this person that's pushing this car to speed up. So I'm going to put the car in the system, obviously, and then the question is, do I put the person in the system or do I not? Now here's the so the answer to that question is you don't want to put the person in the system. The reason you don't want to put the person in the system is because if you put the person in the system, then you have to like figure out what kind of energy did they have initially. And they ate something for breakfast, and so therefore they, have some sort of chemical energy stored up that they're going to use. And so, but that just is kind of beyond the scope of what we're trying to deal with here. So we're going to say, um, the person is not in the system. And why we would do that is, right, what we can do is we can just have the person do work on the car, meaning that they add energy. So that's from the person, right? So it's energy transferred to the car from the person. Now I don't need to figure out what kind of energy the person had ahead of time, because they're just not in the system. So I'm not analyzing the energy from that person. Also, if you think about how you'd probably go, the kind of questions that might be asked about this problem, it might ask you about the force times by the distance. And you could calculate the work of the person that way. Then, of course, all that energy turns out to be kinetic energy. So, go. A load of bricks resting on a compressed spring is launched into the air. So probably have the block in the system. We'll also probably have the spring in the system. And right, we're obviously going to have gravitational energy, so we should probably put the Earth in the system. Okay, so we have zero gravitational energy, zero kinetic energy, all elastic energy. So there we go. Then here we have some kinetic energy, some gravitational energy. So I'm just going to split those four between kinetic and gravitational. Any split absolutely would be fine. 3 kinetics, 1 gravity, obviously 2 and 2, 1 and 3, that would all work. Next up is a crate starting from rest is propelled up a hill by a slightly coiled, tightly coiled spring. So obviously let's put the spring in there, block in there, and again, we're going to have gravitational energy, so we're going to have Earth in there. So again, with all elastic energy, and then the end, some combination of gravitational, kinetic, and gravitational energy. Now, you might say, well, it's still on the ground, and that's true, but it is up higher, right? It does have some change in height. So even though it's still on the ground, it does have gravitational energy. The other way to think about this is like, obviously, it has some gravitational energy because if I put like a little ball here on the top, right, it would gain kinetic energy as it rolls down. That's so that it must have had gravitational energy at the top of the hill. So even though it's still on the ground, it can still have kinetic energy. Okay, next up, for number 7, I would recommend that you just choose this to be h is equal to 0, meaning that it has 0 gravitational energy when he's kind of all the way stretched out. So he starts out with all gravitational energy. Oh, I suppose we could put person in the system. We should also probably put the bungee in the system, and we should probably put the Earth in the system because it has gravitational energy here. And starts out with all gravitational energy. At the end, it's all elastic energy, and that's why, right, it makes it a little bit easier if you say h is equal to 0 when he's all stretched out. If you didn't, then you maybe have like 1 bar in gravity and then 3 bars in elastic energy, and that's fine. There's nothing wrong with that. This is just an easier way of doing it. And since you can pick h to be equal to 0 anywhere you want, um, that would be kind of what I would recommend. All right, let's go ahead and take a look at the last one. So in this last one, we have a train here. Train is moving very fast, so obviously train in the system. And basically Superman, Superman stopping the locomotive is pushed backwards a few meters. So what I would do in this case is put only the train in the system, and right, obviously it starts out with quite a bit of kinetic energy, and then I would just right if that's the only thing I put in the system, I don't need to worry too much about where it goes. Um, but you could say to Superman. So, basically all that kinetic energy is being transferred to Superman. It also could be transferred to the track. I don't know that we need to be that specific, but basically that's energy that's leaving and leaving the train. And as long as we just use the work out there, then we don't need to talk too much about specifically where it's going. Though it's probably again some combination of Superman. So hopefully this helps you kind of go through and determine whether your answers are correct. Again, they don't have to match exactly, but hopefully as you listen to me talk about it, you can kind of determine whether yours is correct or not. So thanks for watching. Hope you found this helpful.